Okay, now on to this episode's papers section. In today's episode, I'm only going to focus on one paper, and it's a little bit of self-promotion. I'm the lead author on this paper, and it's entitled Impact of Topographic Change on the East Asian Monsoon in Japan and Eastern Asia During the Last Glacial Maximum. And this was published in Progress in Earth and Planetary Science back in February. So, some background on this paper. Basically, this paper has its beginnings back in around 2018 or so. At that time, I was looking for a way to move to Kumamoto, and where I am now, and I met up with Dr. Tomita, who's a professor at Kumamoto University, and he's kind of a meteorologist, and he focuses on the climate, present-day climate in Eastern Asia, specifically the summer rainy season, which is related to the monsoon. And at that time, I was working in the Alfred Wegener Institute in a paleoclimate modeling group. And so anyway, I thought, how can we work together on something? So we thought, well, let's look at the East Asian monsoon at the last glacial maximum. So first thing I did at that time was to download some of the climate models from the last glacial maximum, which was about 20,000 years ago when the ice sheets were at their maximum extent. And one thing that really came out from that activity was that there's tended to be a large precipitation anomaly centered over the East China Sea, and in some cases into Western Japan. So that kind of piqued our interest, and the hypothesis about that is that this is likely related to topographic changes. And at the time, I was also trying to make connections with colleagues at the University of Tokyo. So all of these things together, we decided that this would be a good project to work on. It's like, what's causing this precipitation anomaly in the summer monsoon in Eastern Asia? So as a bit of a background, of course, I'm mostly, in most of my activities, is focused on ice sheets and topography reconstructions and sea level change. So I'm not specifically a climate modeler, but if you look at the topographic changes from my reconstruction paleomist, you'll notice that the continental shelf areas along the eastern side of Asia are pretty much exposed during the last glacial maximum due to a drop in sea level on the order of 120 to 130 meters. And one of the consequences of that sea level drop is that, of course, the East China Sea is almost completely land during the last glacial maximum. And the other component that's interesting is that the Sea of Japan, which is mainly connected through two straits, the Tsushima Strait in the south and the Karu Strait between Honshu and Hokkaido Islands. Those are the only two ways for Pacific Ocean water to get into the Sea of Japan. So if sea level drops, the Tsushima Strait is effectively closed off to Pacific seawater. And to try and test the effects of this, we came up with modeling experiments using ICSM, which is a climate model that allows you to also measure changes in isotopes such as oxygen isotopes. So oxygen isotopes are typically used in paleoclimate reconstructions. So for this experiment, where we were mostly interested in the effect of the topographic changes and the sea level drop, we did modeling experiments where we took a pre-industrial, which is to say a climate model simulation that's before the rise in carbon dioxide, like about 150 years ago. And we modified that experiment just with the topographic changes. And the reason we do that is that at the last glacial maximum, there's a lot of other things going on, like the Earth's axis of rotation is a bit different, the orbital configuration is different, and there's the ice sheets are there, and there's also lower CO2. So if you have too many things going on in your climate modeling experiment, it's hard to isolate a single thing. So with that, we tested out what the effect on precipitation is, and we checked the winter precipitation and the summer precipitation. And with these experiments, if you lower the sea level, then there's a rise in the precipitation in the East China Sea and around western Japan. During the winter, there's a drier conditions, so it appears that if you isolate the Sea of Japan from the Pacific Ocean, it effectively shuts off the winter monsoon precipitation in Japan. And if you look at the temperatures, it sort of gives an explanation as to what's going on. So the sea level drop in the winter time, it causes the exposed shelf areas to become a lot colder in the winter, which makes sense because all of a sudden you go from having ocean water to land, and land will cool down more in the winter, and it's the opposite in the summer. Dry land will warm up more than water. So basically what's happening is that the precipitation increases where it's a bit where there's land, which is what happens in the East China Sea. And in both seasons, though, the Sea of Japan is colder, and that's a result of the lack of warm Pacific water going through the Tsushima Strait. And so if you have a colder colder Sea of Japan, you're going to have less precipitation when the winter monsoon happens. We saw kind of the opposite situation during the winter last year, where the Sea of Japan, the surface temperature of the water was really warm, and when the monsoon came, there was a lot more moisture to pick up, and in some places there was record-breaking snowfall. When we compare with some models of that have all of the components of the climate system changed for the last glacial maximum, the Alfred Wegener Institute group that I work with and the University of Tokyo group I work with both use the paleomist topography reconstruction to do some climate modeling of the last glacial maximum. And if you look at the results, the Alfred Wegener Institute model, AVI-ESM, has this precipitation anomaly over the East China Sea, whereas the MIROC, which is the University of Tokyo model, does not. And I found out the reason was that in the MIROC simulation, they only changed the ice sheet height. They did not change the topography in the East China Sea. So that really demonstrates that if you don't have this topography change, you won't have the change in precipitation. So I thought that worked out quite well. I was also interested in looking at the paleoclimate proxy records. So I compiled the oxygen isotope proxy records from speleothems, which will have will measure the effect of changes to precipitation as well as planktic foraminifera oxygen isotopes records, which measure the conditions at the surface of the ocean. And depending on where you are, the anomaly between the last glacial maximum and the late Holocene, it varies a bit. And for the Sea of Japan, though, there's a large negative anomaly in terms of the oxygen 18 anomaly. So I was interested to see if that could be replicated in this model that only considers the topographic changes. And that was the case. Like, if you just isolate the Sea of Japan without changing any other parameter in the climate model simulation, you do find a negative anomaly of the oxygen, delta oxygen 18. So it does show that the lack of Pacific Ocean water going into the Sea of Japan will cause this oxygen isotope anomaly, which is recorded in these proxy records. And that'll be primarily a result of the fact that the water is colder, as well as you'll have a lot more rainwater getting into the Sea of Japan that's not flushed out the other way in the Tsugaru Strait. And the rainwater will have less oxygen 18 than seawater. So those two things are probably contributing to this anomaly. And the reason I was interested in that is the oxygen 18 proxies go back about 400,000 years at right now, and you can see that there's a sharp negative anomaly whenever there's a large glaciation. So there's probably a threshold sea level drop when you have the effective closure of the Tsushima Strait. And if we find out what that threshold is, then we can use that sort of as a sea level indicator. So I was happy to see that result. So, of course, this study, I couldn't have done it without all of my colleagues at various institutes. So, of course, Dr. Tomita at Kumamoto University, who supported my Japan Society for the Promotion of Science postdoc fellowship, and of course Xu Zhang and Yong Soon. So Xu is my main collaborator for many paleoclimate studies, and he helped me out by doing these ICSM experiments. And of course, my colleagues at Alfred Wegener Institute and University of Tokyo. So they've all helped me out over these past few years to get this study done, and it was definitely something different than what I'm used to, but I also learned a lot. I learned so much about climate modeling, which I can now express in some of these podcast episodes. So that's it for episode 6 of the Raised Beaches podcast. And with any luck, the next episode will happen before the end of the summer, but we'll see. We'll see. Anyway, stay cool and stay healthy. Okay, bye.